Get out.
Carlos, ya abro la reunión.
I'm going to tell you which schedule you are going to take. In order to
Carlos.
clear the vision with our online weeks. Okay. So welcome and my colleague Carlos and yes.
Hello. Hi. Nice to meet you.
Carlos.
Hey, how are you? Nice to meet you. Please go ahead. Hola. Hola, Liz. ¿Cómo estás? Hola. Hola. Buenos días. Hola. Buenos días. ¿Qué tal? Buenos días. Hola. ¿Cómo estás? Hola. ¿Cómo están? Tú me avisas, ¿no? Cuando me digas. Okay, so welcome to the time and frequency division. My name is Carlos. Also, welcome to the virtual visitors. It's a pleasure for us. I'm going to explain you some details behind the best standard of time in Mexico in general. So our main objective here is generate and disseminate the official Mexican time. To do so, we have to generate the basic or the base unit of time in the international system of units, which is the second, as you know. Obviously, the international system of unit is very important in National Metrology Institute. So this facility is kind of a factory of very high quality seconds, right? We are talking about seconds of an uncertainty of 1 part in 10 to 15, which is really incredible. And as you know, is the best quantity that you can measure in the international system of units. Please don't hesitate if you have some questions. Please interrupt me. It's not a problem to create a dialogue or something like that. Well, so far, the question now, everything a problem is in just the moment. Okay. Let me solve a problem here. Yeah. Okay, maybe I can change the slide. Okay, so the question now is the reason because we have to produce that kind of seconds. We're talking about 1.14 zeros, and we have our uncertainty in the digit number 15. So if you think in for a national time, for an official time, you don't need that kind of seconds. Is that correct? You need maybe some hundreds of seconds, milliseconds, or something like that, right? So we have seconds of some parts in 10 to 1 or maybe 10 to 2. And here we have seconds of an uncertainty of 1 part in 10 to 15. The reason to do that is because we support or want to support a lot of applications. right? The most important application that we want to support, or we already support, is the communication sector, which demands really, really good seconds. So it's very important for the productivity of a country produce this kind of seconds. So that is the first and natural question of why we have to produce this kind of high performance seconds, and the reason is because the applications. However, the reason to be here is because the official Mexican time. Well, so the applications are in different sectors. We have applications like 5G networks in telecommunication sectors. Also, there are important applications in the financial sector. The stock market now is not using human traders anymore. So now a software is synchronized to an official time, and then dividing a second in million of parts. They have to buy and sell different values, right? That is the idea. In the electrical sector, these kind of seconds are also important because we have to we want to sell and buy electricity, and to avoid a destructive interference, for example, we need a really good synchronization in the network, right? Also, if we want to implement some fault detection, dynamic billing, and things like that, is very important, the synchronization. And the last application, which is very interesting here, is the blockchain. Do you know something about blockchain? Of course. The blockchains is really, the time tax in the blockchain is really important, because depending on the quality of the time tag, you can improve the quality of the blockchain application. So again, the time is in all of these sectors and is very important. Yeah, you have a question? Yeah, please.
Like you were talking about the blockchain, for most of the applications you mentioned, I can understand why one time, not just time interval, but synchronized. But for communication, my question is about communication. It's also there that they want, synchronize with the actual time, not just with a frequency, not just with an accurate interval.
Are you talking about telecommunication networks?
Yes, or 5G,
Yeah.
just generally. I don't know the details of the application there. Do they need to know the actual time, official time?
Yeah, in fact, is really important. Maybe the official time is not as important of the synchronization, maybe, but in the telecommunication networks, we use the TDMA technique, which is time multiple division access, right? So if you have a really good synchronization, you can increase the velocity of transference of data and the bandwidth. So the answer is yes, but the telecommunication networks also need tuning and synchronization. So there are two important parts. As you mentioned before, the frequency is very important for the different equipment that they have, but synchronization also is important. So tuning and synchronization.
I see.
Yeah. Okay.
Thanks.
You're welcome. Okay. So different applications are really important, and so far I hope I have convinced you about the importance of high quality seconds. I think so, right? because for us it's really important. It's really important to explain what is the reason to create high quality seconds. That is a really, really important task for us. Well, now the question is how to generate 1 second. What do you think about that? Do you have some ideas? How to create 1 second? Yeah, yeah, you have a really good idea. So the answer is here in the international system of units. As you know, we have 7 base quantities, 7 defining constants, and 7 base units. Now we are talking particularly about time, and the defining constant of time is the separation between 2 ground states of the hyperfine structure of cesium 133, which is the unique stable isotope of cesium, right? So the question now is how. And another question is related with why we have to talk about frequency and we are not talking about time. That is a really important question here. So the answer is related, connected, excuse me, with the equation that says that the period of a frequency is inversely proportional to the frequency. So we can create time intervals using a frequency, and that is the best solution because now there is a technical limitation to measure time in a direct fashion, right? What is the reason? With chronometers, we can measure intervals of time maybe till 1 microsecond. And 1 microsecond is a really big space of time for the applications that we are running right now. In Formula One, they can measure 1 microsecond and is sufficient for the application. But now, for example, in terms of the telecommunication networks, we need nanoseconds, attoseconds, joctoseconds, and so on. We need really, really, really good seconds. And that is the reason because we measure, instead of the time, we measure the frequency. And again, the answer is because we don't have a technical limitation measuring frequency. We can measure with some simple equipment frequencies between DC levels and some gigahertz, which is enough for this application. What happened? You are trying to change the. No problem. I'm just imagine. Oh, great. Okay. Now I have the control right now. Excellent. So the application, as I mentioned earlier, telecommunications maybe is the most dependent application on synchronization. So our relationship with the telecommunication operators is really close in order to deploy 5G networks, for example. If we really want to deploy 5G networks, we have to use this kind of sector, right? The second one, I forgot that, is the transportation sector. For example, in an airport, if you improve the level of synchronization, you can reduce the distance between airplanes, improving the efficiency of the use of the space in the air and also on ground, improving the service, right? And the use of different resources in electricity. I already mentioned the application. And finally, of course, in the IT sector is very important, the level of synchronization, because we don't have now manual strategies to synchronize different kind of devices. Okay, this is the important one. It's really that is the strategy which is very important for us. We measure frequency instead of time. We don't have any chronometer here. That was really bad for me 10 years ago because I want to discover the best chronometer worldwide. So my surprise was that here there are any chronometer, so we use the frequency, and now you will be experts in time and frequency using this idea. It's really simple, the idea. So we have a frequency, for example, in the case of the figure, we have a wave of 10 hertz, which means 10 oscillations per second, right? So here is the key factor, because we can create intervals of time using a really stable frequency. But now the question is how to define a really stable frequency. The answer is here. We use atoms to define a really stable frequency, but there is an issue related with the spectral purity of the frequency, because the problem that we have is that we have to count oscillations, but there is an uncertainty counting that oscillation. So let me try this example. Here we have 10 oscillations per second, so we have to count 21 zero crossings if you want to create 1 pulse per second, right? So the frequency of the definition of the second, which is the ground state hyperfine transition of cesium, is this very big number, 9,192,631,770 hertz. That is the frequency of the atomic transition. So the question for you guys is how many zero crossings we have to count in order to create 1 second.
These transitions are gravitational field.
Yeah,
True.
of course.
So we're talking about transitions at this space. If we try to count these transitions, let's say in orbit or in Jupiter,
it's different.
they will be completely different. So
Yeah.
it depends where exactly in the gravitational field you're measuring these transitions.
Yeah, of
Right?
course. That is a really good question, because we have a frequency, and this number is an ideal frequency. If you have a cesium isolated atom, we have this frequency, but we have to correct not only for gravitation, we have to correct because due to collisions, black body radiation, and things like that. But the frequency is, in general terms, is this frequency, right? We have to make some millihertz changes due to the local effects in the laboratory. And we will see that in the atomic fountain, right? Okay, so again, the question for you guys, how many zero crossings, let me continue, okay. How many zero crossings we have to count? In fact, this is the equipment that performed that task. How many zero crossings we have to count?
2 times this plus 1?
Plus, no, because look, here we have 10 oscillations per second, and we have to count 21 zero crossings. So maybe you have to multiply by 2, right? So in this case, we have to count something like 18 billion of zero crossings, right? And the equipment which is doing that task for us is this equipment. So if, as you can see here, there is a pulse per second, every second, and the information is from the frequency of the atomic clocks. So we define a frequency using high performance commercial cesium clocks. In fact, we have 5. We have also a hydrogen maser inside the Faraday jar. And the reason is because the transition of the hydrogen is very dependent on local environmental conditions, pressure, temperature, etc. So we have to use Faraday jar. And the last one, and the most important one, is the atomic fountain, because it's the origin of the traceability change for the measurements of time. So, do you have a question? Yeah.
One final
please.
one.
Yeah.
So you're also having traceability through gravimetry, effectively. You need to measure gravity.
Yeah. In fact, we did gravity measurements in our laboratory to correct that effect. But if you think in the uncertainty that we have, that effect is not relevant. We evaluate that, but it's not a big effect. But yes, we evaluate that. Thank you. Another question?
You said that you have here 5 cesium clocks, and are they managed in parallel, or do you use just one, or how do you take the average value of this set of equipment that you have available?
Okay, that is a really good question. In fact, we have 5, but in the time scale, we have 3 cesium clocks, the hydrogen maser, and the atomic fountain. So an algorithm creates something like a virtual clock, which is the best representation of every member of the ensemble. That is and the real signal of that time scale is the UTC CNM, and that is the quality of the seconds that we produce. That was the question, right?
And this price is defined by CENAM, or it comes from like the report you produce daily or monthly to the BIPM?
Okay, we have time is really different quantity, as you know, Liz, because we have a continuous key comparison, right? With every second, our measurement, we send our measurement to the BIPM, and every month we have a report about that measurement. The name is circular T, right? So we can take some decisions based on the results of the circular T. But here we have an atomic fountain, so we can make a real-time comparison every day, every hour, to make more frequent correction. Yeah. Thank you. Okay, more questions? No?
Yeah.
Because we are online.
Yeah. Related to the atomic fountain, do you turn on 24 hours, or how do you link with the other clocks?
Well, now we are trying to improve the time that the atomic fountain is operating. Now it's only maybe 2 or 3 weeks per month, and when we have the atomic fountain operating, we make a correction per day, only one per day. And we are, as you know, we are trying to make some experiments related with if it's a good decision, make one correction per day, or 2, or maybe every 2 days, or things like that. We are actually trying to understand that to improve the local time. Do you have also a question, right?
What is the support about the electric energy in this area?
In terms of time, or
for support the electric energy all equipment.
for example,
Yes.
yeah. Well, we have 4 different options to avoid a loss of electricity here. The first one is a UPS system, an intelligent UPS system, and then we have another system to avoid a loss of energy, because it's really important in terms of the application of the official Mexican time that we don't have that kind of problems here, right? Yeah.
Thank
Okay. Ana? Okay. More questions? Or so here maybe is an important question for us. What is the role of time and frequency groups around the world? So the answer is generate the best possible seconds using state-of-art techniques, which means commercial and atomic clocks. We will visit a lab clock, which is the atomic fountain, to show you how to create really high quality seconds. So the other problem that we have is that we have to generate seconds, but we also have to disseminate that seconds. There are two important tasks for us, and depending on the application, we have landlines if you want to synchronize your clock. If the application is more demanding in terms of times, we can use this kind of NTP servers. In fact, we have two of them. And if your application is more demanding in terms of time, we can use satellite systems, optical fibers, and things like that, depending on the application. So that is the reason, because here is that our job is disseminate it using a variety of mediums, RF, which is microwaves, optical fibers, satellite techniques, cables, etc., according with a specific application. So build synchronization networks by delivering timing information via transport networks using a sync protocol. Now, CENAM is trying to create a national synchronization network, just to avoid the problem that you mentioned earlier about, for example, the energy. So if you have different nodes of really good seconds in Mexico, we can deliver for different applications with some techniques as I mentioned earlier. So that is the main idea of our lab. So maybe now we will move to the atomic fountain, right? Okay. So this is my card. So please scan this QR code, because we have 4 interesting videos related with our job and things like that. So please share, follow CENAM at YouTube, because it's really important for us trying to disseminate the importance of time in the economy in general, right? If you have more questions, please. Yeah. Yes, because the in real time there is some delay in the transmission to the displays. Yes, but no, but this is the local. This is the UTC time. It's not the. Are you talking about the seconds? Yeah. Yeah. Because this is the local time at the Greenwich Meridian. Yeah. Okay. So,
When you disseminate, synchronization becomes an issue if you disseminate over wires, for example.
Yeah.
It takes forever compared to 10 to the 15th. Do you send along do you build in a correction factor based on the transmission distance, or how do you address the fact that
it's a really
it takes a
challenging
long time
task
to move an electronic signal, or it even takes a long time to move a photon from here to the other end of the country?
Yeah, yeah, yeah. It's a really it's a very challenging problem, because if we want to disseminate seconds with a quality of some parts in 10 to 15, as you mentioned, we have to use optical fibers. And a better option is create an atomic clock that you can move around the country, or create the national synchronization network to avoid the distance. But now we are working in that really, really challenging problem for us.
Okay.
Thank you.
Thank you.
Yeah.
Oh, you, no.
And because, of course, you're generating obviously amounts of data, substantial amount of data, and also it's safe to assume that digitalization for you is something that's ongoing, and you're already way ahead. Yes.
Yeah. It is. It's a big issue for time and frequency, because each second we are comparing every clock respect to every other clock. So yes, we are making some phase measurements in almost real time, and we have a huge of data. So we have to use digital tools to check data, to move data, to send data, to understand the data, and things like that. Yes, this is a very important part for time and frequency.
So it's the opposite, rather than you try to fit in digitalization. Digitalization is part of your nature, effectively.
Yeah.
Yes.
Yeah.
Thank you.
Thank you very much. We have a question from our colleagues of outside. Falas or Fallas, I don't know. Fallas Cordero, Oscar. Can you please turn on your microphone and ask to my colleague Carlos?
Yes, thank you. Can you hear me?
Yes, we can hear you.
Yes, I hear you.
Okay, hi Carlos, how are you doing?
And I know you.
Is everything okay?
Yeah.
Okay,
How
excellent.
are you?
Carlos, it just fine. Thank you. Carlos, we just talked in the past about this solution for synchronization in terms of network for 5G. Have you been working with or considering some PTP solution for this, for related with 5G and that kind of future technologies, or you are just applying the ones that you show us?
Yes, Oscar, thank you. We are trying, we have some experiments with PTP, as you mentioned, but we are trying with lot of resources, try to create the synchronization network to avoid the transfer problem that we have in time and frequency. And yes, it's the same strategy that we discussed in the past.
Okay, thank you.
Yeah.
Good to see you.
Thank you very much. And also to our colleagues online, you can ask anything, open your mic, and here we are for you. I have a question and a comment. First of all, a comment. As we saw in this seminar, we are trying to include digital transformation to metrology, right?
Mhm.
And time is very important.
Yeah.
The time reference, because if we want to talk about a grid of sensors or interoperability in the streets with intelligent vehicles or automatic vehicles, we need to communicate all the systems and sensors in real time. So that's why we need a very precise time reference.
Yeah.
Can you give more explanation about this? Or?
Yeah, the problem, because we are here, is just that real time work. That is a nightmare for the application, because real time means a high accuracy level of synchronization. For example, if you want an autonomous vehicle, you need a really good synchronization if you want to deploy that kind of application. So the answer is yes. We need in fact, we are here because of all of that application that need really good synchronization, and we are working to improve the level of synchronization for 5G networks, blockchain applications, and another physical really interesting for test gravity, for example. You can use clocks if you want to test the relativity theory of Isaac Newton. Of Albert Einstein. Is amazing. We are in a really good moment of the history because we can use clock for almost everything. So the challenge is how to create a link between some variable and the frequency. That is the challenge right now. Thank you.
Thank you, Carlos. And a question, in security, do you think time can be used to digital signatures?
Yes. In fact, we have in our value chain, we have a service to the time stamping authorities. So if in Mexico, if you want to create a bill, you need to know who did the transaction and when the transaction happened, right? So that in that point, we use the service of time stamping authorities, and the time stamping authorities are synchronized to our really high quality sector, right?
Thank you.
Yeah, please.
I don't know what level of accuracy different groups at CENAM need, but do you provide support of time and frequency to other activities at CENAM?
Yeah, of course. That is an important part of time and frequency because we support time-dependent variables, and the time-dependent variables are maybe all the variables, except, for example, the mole, but we support length, mass, temperature. Yes, the answer is yes.
How do you deliver? Do you have some fiber network, or do you calibrate equipment, or how do you provide the support?
Using the two strategies. One is some calibration of equipment. And we have, for example, an optical fiber link between this building and the L building for the Josephson effect to create that kind of traceability to the unit of time.
Okay, thanks.
Yeah. He has.
We have a question online, so later.
What is the expected time of life of each clock?
Excuse me?
The expected time of life of each clock?
Oh, 10 years.
10 years.
And well, that is a really big issue for us because the atomic clocks are really expensive. Here we are talking about $100,000. The hydrogen maser, maybe $500,000, and the atomic fountain, no cost. This is really, really, yeah. But in metrology, as you know, we are trying to improve the economy of a country, delivering the best practices, equipment, and techniques in terms of metrology. So yes, we have to use a lot of money, but we have a multiplicative factor for the economy of different nations. So that is the reason of the National Metrology Institute. Yeah, please.
I think you have online question.
Yes, okay. Please, Juan Jose Mendoza, can you open your microphone?
Okay. Good afternoon. Do you listen to me?
Yeah.
Thank you. Juan Jose Mendoza from Bolivia is talking. I have a question. Have you developed an application to monitor your session clock source? Do you have an application to monitor the values that you report to the BIPM?
Yes, Juan Jose, thank you for your question. Yes, we already have software because we need to know almost in real time how how is the metrological performance of every clock to increase or decrease the statistical merit of each clock in the atomic time scale. So the answer is yes, we have that. And in fact, we have an algorithm to monitor in real time all of our clocks. We are talking about 4 high-performance cesium clocks, 1 hydrogen maser, and the atomic fountain. Is that your question? Yeah.
Yes, that's all.
Okay.
Thank you.
Yeah, thank you.
Okay, so your fiber coupling, obviously, time is important for Josephson, obviously.
Yeah.
But do you also fiber couple for a frequency tracking, frequency stability of lasers, for example?
We are working on
You're
that.
working on it.
Yeah.
Yeah. Okay. We're on the same boat. Okay. Thank you.
Yeah, because that is a really important question because as I mentioned earlier, it's important synchronization, but tuning is also important for example, the radio frequency measurements. They have a really good traceability to be sure that the frequency is the correct frequency.
Sure, sure. Even for our cable balance, when we need to track, when we use interferometer to measure the velocity of the coil, we need to make sure that the frequency is absolutely not drifting, and if it does drift, by how much?
Yeah. For example, in very long base interferometry,
yes,
we was last 2 weeks in the big telescope from Mexico to observe the black holes. They have a really, really good source of time and a source of frequency. So they need synchronization and tuning to be possible that observation of the black holes.
You need to synchronize, time, through all the radio telescopes around the Earth to capture, that black hole, otherwise, without you.
Yeah, that is really, really, really interesting for us. Thank you.
Okay, I think we can continue. We don't have. Falas Cordero again.
Okay.
Please go ahead.
Carlos, have you think or developed something related with frequency comms?
Yeah. Yes, Oscar. In fact, we have 2 frequency comms, and actually we are calibrating the lasers for the guise of length. So yes, we have. In fact, here, can you see the screen? Here is the image of our frequency comm, and we already calibrate 4 lasers from dimensional metrology division. So yes, now we have the national reference of optical frequency.
Okay, excellent. Do you have published something related to a paper
No,
or
yet.
no?
No,
Not yet.
yet. We are preparing something for the community. Yeah.
Okay, I wait for it. Thank you.
Yeah, thank you.
Thank you very much.
Okay, so let's move to the atomic fountain.
Yes, please follow me.
Sí. Adelante, por favor. Oscar, sí. Sí, Oscar es un viejo conocido.
The first 5 colleagues, please, you're going to enter to this wall and you watch the interferometer, and the next follower 5 to follow me, please. Be careful with your head. Oh, maybe you can, yeah, you can be there. Yes.
Sí, se pueden ver por ahí.
Be careful with your head. Please come.
Don't come.
To the side.
This is our big clock. Son como 15 años. Ya, son como 15 años más o menos, 15, 17 años de desarrollo, pero sí, yo la última parte yo estuve por ahí trabajando en las fibras ópticas, en mejorar la estabilidad del láser. Okay, Oscar, so it's okay. Everybody is it's okay. Now the clock is not operating, so there is no problem with our visit here. But this is a clock. The name of this clock is an atomic fountain, and the objective of this clock is trying to achieve the conditions of the definition of 1 second in the International System of Units. So high performance cesium clocks have atoms at room temperature, and some problems with the collisions between atoms are really problematic for us when you want to create really good seconds. So in an atomic fountain like this, you can create seconds of some parts in 10 to 16. So it's amazing that there are maybe less than 20 experiments of this kind in the world. And this is very important for us because we can make some corrections to the UTC in almost real time. We don't have to wait for the circular T. We can make a lot of experiments trying to find the best way to correct the UTC time scale. And that is the reason to create this kind of experiments. Of course, the generation of knowledge and different measurement techniques that we have developed here at CENAM. That is the idea. So the experiment is not really complex. Believe me, it's not really complex. But here we prepare the light, and here we have a low pressure atmosphere of cesium atoms in the metal cylinder in my left side, right? So we want to. This is really really interesting. We want to trap the atoms and cool the atoms, and to do so we use light. So we send light in the x axis, in the y axis, and the z axis, trying to create a three-dimensional space to manipulate quantum states of the cesium atom. That is the idea of the atomic fountain. So the reason of the name is because it's like a water fountain. It's the same. So we trap the atoms in this, maybe the height is this, and then we send the atoms to a microwave cavity to interrogate the microwave transition, which is 9,192,000,000 and so on. Remember that number if you want to go to your home. Is the password for CENAM, right? Okay, so that is the reason of the name. Is an atomic fountain because the atoms are moving in this vertical trajectory to interrogate the hyperfine transition of cesium, and in the descending trajectory we detect how many atoms did the transition, and according with that information we correct the frequency. Of course, we have a shift of the frequency due to the local gravitational potential, collisions, black body radiation, and in fact we have to create an uncertainty budget to evaluate every aspect of the different physical phenomena that affect the experiments. So far, do you have some questions? You are now experts in time and frequency. Yes, please. Maybe they need the microphone to make the question.
Oh, I grabbed the microphone before you, but
You have. Please.
What pressure are we talking about now? How low?
10⁻⁶.
So near, all right, okay.
Yeah, that is the pressure that we have. And only, the idea is that we have only cesium atoms in that environment, right?
But it's pressure dependent, of course. So you need traceability from pressure as well. No?
No,
to know
really,
exactly the pressure value.
No, really, because we only need to be sure that there is only cesium atoms. And with this laser, we can only interact with the cesium atom. So if there is something else, there is not a big problem for us. So yes, thank you. Do you have another question? Yeah, please.
just two questions.
Yeah.
First, for the cesium vapor, where do the cesium atoms come from? How are they generated?
Okay, that is a really good question. Is this, in fact, the isotope is the cesium-133, which is the unique stable isotope of cesium. You can buy that as you can buy another element. I think that is the number 8 or 9 in the earth in terms of the abundance, I think. But the extraction process, I'm not sure how to extract this.
But when you get it, you have it in a piece of metal and you heat it or something like that?
No, we use kind of this. So inside, we use gas in the gas state, right?
Okay.
Yeah.
And sorry, the second question, where is the microwave cavity?
The microwave cavity is inside the flight region. This is the flight region, the metallic one.
Okay.
This is the flight region. And to this side, we have a microwave cavity tuned to the transition of cesium, which is 9,192,631,770 hertz. That is the number. That's the password. Please remember that, because that is the Wi-Fi password. When you go to a time and frequency laboratory, that number is used for a lot of things. Yeah. More questions? Yeah, you're welcome.
No, I think no.
No. Okay, so let me explain more about.
Oh yes, sorry.
No?
Sorry, Carlos. Yes,
You don't have time?
again, Falas.
Oh, okay.
Go ahead.
Oscar again.
Oscar.
Carlos,
Yes. Yes.
In terms of the definition of the unit and regarding your experience developing this kind of clocks, what is your opinion, or how do you consider this is going to impact this kind of works? Because we're talking about develop in terms, especially in terms of comparison, right? Because we now we the techniques we have for compare our reference works in and it's not depending on the GPS. But if we are talking about optical clocks, the things what's work.
Well, so thank you, Oscar. Let me explain or answer your question. First, CENAM is working to find some budget to create a strontium clock because of the redefinition of the second. As you know, now we are trying to find higher frequencies, and we think that the strontium atoms is a good candidate to redefine the second. So now we are working to find some budget to design that clock at CENAM. And related with the comparisons, yes, as you know, it's a really challenging topic in time and frequency. And maybe the best approximation that we have is the common view technique, as you already know. And we are trying to make some optical fiber links, for example, here with the Simvestab, trying to prove how to compare two clocks. That is our idea, that the ideas that we have related with comparison between clocks. But yes, there are a lot of challenges related with that. And also, we want to construct also a portable clock, but it's so expensive for us. It's so expensive. Yeah, thank you, Oscar.
Thank you, Carlos.
Yeah. Yeah. Okay. Okay, well, let me explain a little bit more about the experiment. So this is the source of photons. This is an ultra-stable laser, which the frequency is 354 terahertz, which is 852 nanometers. And this is the laser that we use to manipulate the quantum states of cesium. So this is a semiconductor laser. So the first step in the experiment is try to filter the principal mode, which is the mode that we use to interact with the atoms. And then the light goes to the experiment. And as you can see here, we have an optical fiber for X, for Y, and for Z. And that's it. We have a magneto-optical trap to combine the effects of a magnetic field and an optical field to cool and trap the atoms. That is, in general terms, the idea of this experiment. We cool the atoms to 900 nanokelvin, which is a really low temperature. And the idea is to recreate the isolation of the atoms, because if the kinetic energy is reduced, we can consider that the atoms are at rest, right? Obviously, it's not possible to be atoms at rest, but this is an approximation to the ideal conditions of the definition, which present, for example, the challenge of only use one cesium atom, which is impossible in a real application. So we cool the atoms, trap maybe 100 million of atoms, and then send to the microwave cavity in order to interrogate the hyperfine transition of cesium-132. That's it. It's a really, really tiny explanation of this experiment because there are a lot of details behind this huge monster, but it's really, really, really interesting for us. If you have more questions, please go ahead. No, in Spanish, please.
I think there is no questions online. Oh, yes, Juan Jose Mendoza, please.
Carlos, excuse me. For dissemination, you are using an NTP server, and what kind of NTP do you use for dissemination, please?
Yes, we have NTP servers. Maybe I can share with you the reference of the servers. Are I think I did not remember the brand of the NTP server, but yes, we have 2 NTP servers. Maybe later we can talk about that if you want, with the particular details of our service and the equipment that we use for that. Thank you. Yes, please.
Thank you.
The microphone.
Probably not everyone can see, but I just want to ask about a couple of components.
Yeah. Go ahead, please.
Why is that one, that fiber so thick? What is that? And I mean that, yes. And
what is the reason of this?
Yes, and also I'm wondering what this silver box is.
Yes, the reason is because to be sure that the frequency of the laser is the correct frequency to interact with cesium atoms, we make here an spectroscopy technique. The name is modulation transfer technique. Maybe is the most sophisticated technique to be sure that the frequency is the correct frequency. So here we create an error signal to lock the laser to that frequency, and then we send the light to the flight region. That is the reason. And this metal is mu metal, and the intention is try to avoid the magnetic fields inside the cesium cell because of the CENAM effect, right? So if you don't have this kind of equipment, we have a signal error which is changing with the magnetic field. So it's really challenging. And the reason of this is because with temperature, the optical power of the light sent to the spectroscopy technique is fluctuating. So this is a local solution, a Mexican solution for to avoid that effect. That is the reason.
Thank you.
Yeah.
And what's this part about?
Yeah, that is the same because we have, this is the master laser, and we have over there a repump laser. Because we need to repump the states of the atoms to maintain the cyclical transition. So we use a DFB laser. It's a normal laser, right? And we use another spectroscopy technique to be sure that the frequency of the repumping laser is the correct one. So we create an error signal here and lock the laser to the transition to be sure that the repumping is happening at the correct frequency, right?
Okay, thank you.
Yeah, thank you. Yeah, that is the repumping laser, and this is the master laser. Yeah. So the line width of this laser is 2.3 kilohertz. So the line width is a really good laser. Yeah. amazing of this laser. And the idea is try to avoid some instabilities due to the light when we try to manipulate the quantum states of fission. Yeah, yeah, yeah. And that is an important problem. For example, if you want to build an optical clock, the challenge that you have is that the transition, the line width of the transition is lower than the scission transition. So you need a more sophisticated laser in terms of line width, for example. That is a really, really big challenge. Yeah. I'm talking about less than 100 hertz of line width.
Oh, sure, yeah.
It's really, really tiny.
Thank you.
Okay, you're welcome. So now you have to say the password. What is the password?
9 billion.
9,192,631,770 hertz. That is the frequency of the hyperfine ground state transition of cesium 133. Yeah? So you are experts in time and frequency so far. Yeah.
Now that you've told us that, I realize what comes after the decimal point? Is it all zeros or for the frequency?
For the frequency, that is a really good question. Ideally, zeros. But for example, the local frequency that we have is 3 zeros and 1, 2, 4. That is the local number of the frequency due to potential effects here, right?
But we don't need to remember that together.
You have to remember that. It's the password. If you want to go to return home, you have to know that number. Thank you very much for your visit and welcome.
Thanks, Kevin.
Yeah, no, I think. Thank you very much to everyone, online colleagues. This is the last time, last chance. If you have some question for Carlos. If not, thank you very much for your attendance. And
Alder, here there is a question.
Yes. Well,
The last one, only for the teacher.
Yeah.
What's the difference between time and interval of time?
Oh, it's a huge difference. That is a really common question here because we cannot create time. The time is over there passing by, and we can do anything. That yes, your precision is really important because we create intervals of time, and the most famous interval is the second because it's the base unit of time. But we can also create milliseconds, nanoseconds, microseconds, and things like that. But yes, thank you. Okay, so thank you for your visit. Do you have a question?
Yes, one question, Carlos.
Wait for the microphone. Yes. Oh, you have it. Yeah, thank you.
Why is important use the sender source? Other question is when switch on the system.
Okay, the first one, the hyperfine transition is dependent on the magnetic field. So we use mu metal to isolate the external magnetic field, but we need a magnetic field to be in possibility to see the microwave transition. So we have a center reference because we create a controlled magnetic field, a really good magnetic field in order to know what is the separation of the hyperfine levels using that reference. That is one reason. What was the last question?
Switch off the system.
Okay. Ideally, for example, in at PTB Observatory of Paris, the operation of the atomic fountain is continuous, because when you have a continuous operation of a clock, you can exploit all the advantages of this clock, but it's really challenging in terms of optical alignment, for example. That is very challenging. The temperature of the laboratory is really challenging also. And now we are trying to increase the uptime of our atomic fountain to that continuous operation. Now we operate the fountain for 1 week, 2 weeks, and so things like that to make some corrections to the UTC CNM. But the idea is a continuous operation. Okay. And if you want to contribute to the TAI, if you want to correct the TAI, you have to make that your fountain operates for all time.
Okay. Thank you so much.
Yeah.
Okay, so thank you very much. I think this is the end of this virtual tour. Thank you, Carlos, for a very nice explanation.
My English. Thank you so much. Thank you for your visit.
Sorry.
Thank you for our virtual visitors also. It's a pleasure for us. Yeah.
Thank you, Carlos. And also to our colleagues for Metrology Working Group 9 that collaborates with this interactive visit, virtual visit. And well, so thank you very much. And with this, we finish this. Have a nice day.
For you. Thank you very much. Yes. Yes. In fact, there are 9 transitions. When you have a magnetic field, you have 9 transitions, and the less energetic transition is the transition of which define the second.
So
that is the reason, because we have this amazing laser.
More questions.
That is the new generation of
you can ask.
incredible. And to create seconds of one part in 10 to 8.
In the future.
Yeah, and that is the state of art of the time and frequency measurement. Yeah, incredible.
Thanks, guys.
Amazing. Thank you. Nice to meet you.
The new director of
Thank you.
dimensional
Con gusto,
metrology.
Liz.
Oh, yeah.
No, ellos me están esperando, yo creo. Normalmente nos vamos como a la 1. Hola, mucho gusto.
Thank you. Thank you so much.
Thank you.